In this tutorial, I'm going to talk about the mathematics that underlies the derivation of how a damped oscillator moves. And this is important because we care about this for the way electron clouds shake when electric fields hit them. So let me first set up the problem here. As we've probably talked about in class already, we consider an atom to have a nucleus, which we can think of as a point, and then around it there's some sort of electron cloud, which we'll draw in a different color here. And when an electric field is applied, which is to say when a laser beam shines on this atom, the center of this cloud moves back and forth. So it moves back, and sometimes it's pointing to the right, sometimes it's pointing to the left. And we're going to talk about its displacement as a function of time as a vector u, which has time dependence. This electron cloud will slosh back and forth. And we want to know how that will evolve in time. So to figure out how this is going to behave, we think about Newton's laws. We say that the acceleration as a function of time is going to be equal to the sum of all of the forces divided by the mass. Acceleration equals force divided by mass. And there are three forces on this electron cloud. Conceptually, there's a driving force. That's the external laser field. There's a spring force, which in this case is the attraction of the electron cloud back to the nucleus. And there's a damping force. And when we say damping in this situation, we're talking about a loss mechanism. And a loss mechanism here is that as an electron shakes back and forth, it behaves like a radiating antenna, and it will radiate energy away. So that's a loss mechanism. And we're going to now write mathematical expressions for all three of these things. And the driving force, we will say that that's some force F naught, which is determined by the strength of the electric field and the charge in the electron cloud, but we'll just call it F naught. That's the maximum strength, and some cosine, and according to our convention, we'll say cosine of minus omega t, and we will arbitrarily decide that that's in the x hat direction. We'll decide that this direction here is the unit vector x hat. That's supposed to be horizontal. Okay, now that's the driving force. We've got a spring force, which we are used to calling that from freshman physics as minus k. Well, you learned it as minus kx. Now we're writing displacement as u, so I'm going to write it as minus ku. And then there's a damping force, and that's also going to be lossy, so a minus sign, it opposes your velocity. And we're going to write it as some constants, the mass times some constant gamma, and then the velocity. So the greater your velocity is in a given direction, the more the damping pushes in the opposite direction, like wind resistance, something like that. So these are all of the forces, and we divide by the mass in order to get the acceleration. All right, and remember that the acceleration, by the way, is defined as the second derivative of the displacement u. So now we've got a good equation here that we can start attacking. We have to make some assumptions about what u is. So we will assume, and we basically make the assumption that u is going to oscillate back and forth with the same frequency as the driving force once this system has come to a stable oscillation. And what that's really saying is that we're assuming that u of t is equal to some maximum displacement u naught, also a vector, and then a cosine oscillation dependence, which we'll write as minus omega t, And we don't know that it will oscillate in phase with the driving force, so we allow for that with a phi. Now here's where we start playing the complex number game. This, we can notice, is equal to the real of this u0 vector. There's nothing complex about that. And then cosine of that expression is equal to e to the I phi minus omega t. Or we can group these terms a little differently. So we sort of group these terms together, and we say it's equal to the real of u0 e to the I phi times e to the minus I omega t. So the only time dependence is coming right here. So now we want to write the entire equation, Newton's law. We want to write this whole thing as a complex equation. And this is how we do that. We write the whole Newton's law as the real of something, and we just write both sides. So we will say that the real of d squared u, and now what I'm going to do is I'm going to write tilde over this, to indicate a complex u. So I will say that this whole expression inside the bracket, that defines what I'm going to call complex vector u. You take the real of this quantity, and you get the actual displacement versus time. So now this d squared u dt squared becomes the real of d squared u tilde dt squared. That equals the real of the right-hand side of the expression. So we just write that out. We've got f naught, the cosine becomes an e to the minus I omega t. That's how that became that. X hat is just a unit vector. Now k, one thing I'm going to do here is I'm going to emphasize that k equals m omega naught squared. That's just a rewrite of omega naught equals square root of k over m. So I'm going to write that term here as not minus k, but as minus m omega naught squared u. And then the last term, I'll just copy over that damping term, minus m gamma, and now it's going to be the derivative of formally of u tilde dt, and all of this is still divided by m. Now I'm going to take advantage of the fact that time derivatives of u are very simple because it's the time derivative of an exponential. It just brings down a factor of minus I omega, and then I have the exponential itself. So I can rewrite this whole expression. Now I start to take some advantage of the fact that this is oscillatory. A second derivative brings down two factors of minus I omega, and then I just get u tilde itself. I'll write real around the entire equation now. The first term is f naught over m e to the minus I omega t x hat. That doesn't really change this. And then my second term here copies right over, m omega naught squared u tilde. That doesn't change at all, except that I'm dividing by m at the end. So let me just get that m out of the way immediately. My third term is also going to have the m go away. So it's going to be minus gamma, the time derivative, first just one time just d by dt is going to bring down one factor of minus I omega, and then once again I still have u tilde itself over there. And I finally close the braces on this whole thing. I have to take the real of both sides. I'm actually almost done. I just group all of the u tilde terms together and look what I've got. I've got the real of u tilde, and what are my three terms? I've got the one right here, which is minus I omega quantity squared. That's minus omega squared. I've got a minus omega naught squared on this side of the equation. So I'll bring it over here and make it positive omega naught squared. And then I've got on this side I have a positive omega, gamma, and I. So on the other side it'll be a negative I, gamma, omega. Those are my three u tilde terms. What's that equal to? The only term over here is the driving term. F naught over m, e to the minus I, omega t, x hat. I now have an entire complex equation inside of a real operation. I can now manipulate this complex equation in a way I want. I can specifically take all of this stuff and bring it into the denominator of the other side. That way I'm isolating for u tilde, which is what I want to solve for. So let's get u tilde itself. And what will that give me? That will give me, and I'll group my terms here, f naught over m. Then all that stuff over here comes over as a denominator. Omega naught squared minus omega squared minus I gamma omega. And then there's an e to the minus I omega t, and there's an x hat. Now the very last thing I'll do is just emphasize that this expression, now a lot of it on the left hand side, if I take the real of it, that just gives me my vector u. And what have I got on the right hand side? Well, a lot of things are real. F naught is the strength of the force, m is the mass, those are real. Then I have some complex stuff that I've got to remember that I really need to take the real of it in order to get the answer. And what's that? That's 1, I'll write it this way, 1 over omega naught squared minus omega squared minus I gamma omega times e to the minus I omega t. That stuff's complex. And then I've just got a vector x hat. And this here is my solution for the motion of this oscillator. It's not in its totally final form. You still need to take this part here and simplify it, or write it in complex notation, write it in terms of real functions. But this tells us that the oscillation will be in the x hat direction, and this will be the way it depends. And we'll notice that depending upon whether the driving frequency, omega, if it's higher or lower than the frequency of the natural frequency of the oscillator, we'll get different sorts of behavior. I also have a small demo that I'll just end this with from Matlab, and you can see when I play this, the red ball here represents the electron cloud oscillating around the nucleus, greatly exaggerated. It doesn't really go that far. The black line tells me about the force. The red line tells me the response of the displacement. And you can see here that this expression here you can look at is the sort of written in real language is the oscillation dependence on time. And you can change various parameters here. Right now I'm driving the oscillator at a frequency lower than its resonant frequency, 1 as opposed to 1.5. And you can see that the red arrow more than half the time points in the direction of the black arrow. It lags it somewhat. If I drive it at a frequency 2, so that it's greater than the resonance frequency of the oscillator, you can now see that more often than not the response is in the opposite direction of the force. So that's what happens when you overdrive something. And the other thing I will tell you is that if you drive something very near its resonance frequency, then you get the most possible motion that you can out of the system, because the omega naught squared and omega squared are very similar in size, which makes the denominator quite small. But it doesn't move all that remarkably because you still got a damping term. But if I now make the damping very small, like that, now you see it rescaled the axis here. I get very, very large amounts of motion and almost completely out of phase with the driving force. If I now drive it just a little bit under the resonant frequency, now you see that the oscillation is almost perfectly in phase with the driving force. So it really flips around that resonant point.